Now, this is integration. Do you see what kind of integration this is?
Is it going to be another by inspection?
No, it's by
Not.
because we can't, by all means, think about inspection first, but you need to be able to suspect that one part of the product is suspiciously like the derivative of the inner function of the other part, if the other part is a composite. So, but in this case, no, log x, neither part is really a composite, so it's probably not the chain rule.
Yeah.
Since the chain rule is the composite rule. Fine. Anyway, but it is, since we can't work backwards through the chain rule, which is this situation where the inner derivative got spat out, perhaps we're working backwards through. What do you reckon? What am I drawing here?
I remember doing this, but
what I'm drawing is the logical structure of the product rule.
Yeah.
So if we pass, and I do overuse that word, it's a bit pretentious, but on the other hand, I can't stop loving it, this word pass spelt like that.
I've never heard of that.
Have you heard that?
No.
I think it was quite amusing. About 5 years ago, Barack Obama used it, and you could see everybody scratching their heads. It just means pick apart or unwrap or analyze a bit of text.
Okay, I didn't know that. Never.
But it's a good word. You need a word for that, really. Sort of processing a bit of text, and it's crucial integrating how to process that bit of text there as a product. And to think, okay, well, we're going to process it as part of a product rule. Part of the result of a product rule differentiation. So I was taught to think of differentiation as a downward process, going from there down to here.
Yeah.
But if that's the case, then let's fill in the rest of the product rule. And how would it look? What should we put in these spots? So the line here means that I'm guessing that, and this process of guessing, well, with practice, you can look ahead. So looking ahead, well, in a minute, we'll see what looking ahead would have brought us. And this probably is the best choice, to integrate x rather than log. So we'll assume that log is the one left alone here up the top. So we're thinking of this as the derivative of something times log x. So here we would, what do you reckon we'll have here?
Half x squared.
Good.
Yeah.
Exactly, half x squared. And then down here, what should we have?
Is it, what does it derive? Is it what derives from ln x? Or?
Yes, here. We've put that there, which is, do you recall?
1 over x.
Good, yeah.
Yeah.
Yeah, because that's the only power of x that won't integrate according to the power rule, isn't it? Because, then you'd have x to the power of 0 up here, which would be a pain.
Yeah.
And here?
Is it just x?
Except we're not going to differentiate this. We're going to leave that alone, because that's the idea of the product rule. You differentiate one of them and leave the other alone, and then do the same thing the other way around and add the two together.
Yeah.
So here we'll just have?
Half x squared.
Good.
Yeah.
So what we're trying to integrate is x log x here. So how can we make this equal sign true again?
you need to subtract half x squared, or half x.
Half x. You notice it simplifies. Good. And of course, in that case, if x log x is the whole of this bottom row, the integral will be what top row then? We can complete this top row how?
Plus c.
Not yet, because we haven't, then we'll only have this half x squared log x plus c. But then we'll be ignoring this. I mean, the derivative of that is just this much, but we want the derivative to be the whole of this row, because it's only the whole row which is equal to x log x.
Yeah.
So how can we make the top row the integral of all of the bottom row?
Do you minus x squared?
Exactly.
Take the half x. Yeah.
Yeah. So, in other words, give me that again.
Minus x squared. Should give you...
Test differentiating. X squared differentiates to.
Oh wait, that goes to 2x. The x, the half, a quarter x squared.
Quarter x squared.
Yeah.
Good. And then plus c, which you're quite right to not want to forget.
Yeah.
Okay. And that's that. Look at last week's. Did I draw? You see this?
Yeah.
In general, depending on which formula book, what it says in your particular formula book, say, well, one way of doing it is to say the integral of u times v dash. I think that was the way. Which could be written differently, by the way. You know that v dash just means derivative of v.
Yeah, I assumed so, from like f dash x and stuff like that.
Yeah, quite. But in the Edexcel, is it Edexcel formula booklet? I think they write this dv dx.
Yeah, that's what they've written in. I've just found it in my book. It says.
Is it u and then dv dx?
It says integral of u dv dx by
Yeah.
dx with respect to x equals uv minus the integral of v du dx with respect to x.
Yeah. Now the u and v, I think I mentioned last week. Yes, you can do this little square here, and then you can. But all that's happening really is, if you've got u times dv dx. Well, here's why you would have u times v, because v is the integral of that one. And then you would say, and now I'll differentiate du dx and leave b. And then what I'm left with, I need to subtract v du dx. And hopefully, like it did here, this one, v times du dx, simplified to something that was straightforward to integrate anyway. And if it's not straightforward, this thing here, is this how your formula is putting it? Does it say precisely uv minus the integral of
v du dx, yeah.
du dx, which is the integral of that, and then plus c. So that's fine. But again, all we're doing is working backwards through the product rule. So whatever works for you, this is what works for me. So I'll tend to be doing without the u's and v's so that I can just see the overall picture rather than getting bogged down in, this table here, which I regard as getting bogged down, and you might regard as being perfectly sensible, and you might prefer to do, which is fine. So I'll try and do what you want to do. Now then, where were we? Right, here. So x log x integrates to Well, all of this stuff here. We could take
Yeah.
x squared out as a factor if we wanted, or even a quarter x squared. We could write that as
quarter x squared ln x plus c.
quarter x squared outside a pair of brackets, and then put 2 log x minus 1 inside, is what I mean. I'm a bit cramped there. So this top row here, I think, is a quarter x squared times that linear factor there.
Okay, yeah.
But again, it's a matter of taste. I mean,
Yeah.
there's no way a mark is ever going to hang on whether you present your answer like that or like that. No way, no.
Yeah. So it's just, yeah.
So don't worry about that. I'm just saying,
Yeah.
very, you know, in a lot of practical contexts, it will pay to factorize like that to see what you're doing. But
yeah.
Right. Show that the integral of that equals that. Okay. So 1 to e of 1 over x squared log x dx. So how shall we pass it? Do we suspect? Do we suspect chain rule or product rule, basically, is the usual decision? Or, you know, as we also noticed last week, you know, it might just need some kind of pre-processing by means of partial fractions.
Yeah.
It doesn't need that kind of pre-processing, and partial fractions don't look promising here. It probably, you know, we need to decide between chain rule and product rule, really.
Yeah. So how do you decide generally between chain and products?
Yeah, well, we need to look at this and say, is it the result of a chain rule differentiation where I can see a composite and then something else looking suspiciously like the derivative of the inner function? So this got spewed out on the way down.
Yeah.
From the inner function, sorry. Is that the situation here? Probably not, because I mean, you could have 1 over x squared maybe, but then the inner function would spew out 2x, but not a log. Or if the inner function were log, then this would have to have, then we would have, oh, could that work? So, you know, if we just integrate blob, we get half blob squared.
Yeah.
See what I mean? Because the integral of x is half x squared. So the integral of anything is going to be half the thing squared.
Yeah.
We've got that. Oh, nearly. Just not quite.
Yeah. Could you just times everything by 1 over x then?
Well, yeah, but then you have got a more consequential adjustment. Remember before you were worried, and I said, oh no, it's not going to be that worrying. If you multiply by minus a quarter here, you don't have to integrate minus a quarter.
Yeah.
You just multiply the top by minus a quarter as well.
Yeah.
Because of what we said about you know, up or down, integrating or differentiating, you multiply by a constant, you just multiply the other by a constant, that's fine. But of course, why do we need the product rule? Because differentiating a product is, you're not just going to have the product of two derivatives. It's more complicated. You need the product rule. So we can't just bring this up here and hope that it will be okay. If you were differentiating all of that, you'd need to apply the product rule.
Yeah.
So you wouldn't get this. So nice idea, multiply the whole thing by 1 over x, but it's not going to work.
Yeah.
So this kind of does for our theory that this is a chain rule situation. So alternatively, it might be what kind of situation?
Product rule.
Definitely. And it is. So
Yeah.
we'll say, okay, we're down at the bottom of a product rule differentiation. Let's fill in the rest of the product rule. So tell me what to write where.
The
The decision to make is, are we going to have these for the integration and differentiation? Is this going to be the derivative of that and that the derivative of that? Or should we do it the other way around and have, oh, that's helpful, isn't it? Sorry. Or should we have that the derivative of that, like that?
The first one.
Yeah.
Yeah.
I mean, one very good clue here is that we just don't know how to integrate log x.
Yeah.
It's not, I mean, did we say here? We didn't do the 5, did we? But you know, you've basically got 5 basic results, haven't you? You've got ax to the n differentiating to
Yeah.
na x to the n minus 1. Then you, apart from that, it's either going to be sine differentiating to cos differentiating to
minus sine.
And these are basically the only ones we need to know. Ex differentiates to
e to the x.
And log x differentiates. We know how to differentiate log x to
1 over x.
And this is all we need. But on the other hand, what do we do about log if we're integrating log? We haven't got log down here, have we?
Yeah.
There's no likelihood that we could use any of these to integrate log. So we are a bit stuck integrating log straight up.
Yeah.
So
keep log the same.
Sorry?
Yeah. Let's keep log the same and just.
Yes.
Yeah.
It'll have to be that. And it worked out well before as well, didn't it? Because
yeah,
differentiated it, it became nice. Yeah. So here we'll have what?
The integral of 1 over x squared. So it's x to the minus 2.
Good.
So minus third. So 1 over 3x cubed.
Careful though, it's going from minus 2 up to. It's going from power minus 2 up to power
minus 1. Yeah.
1.
Sorry. So let me just do that. X minus 2. So it's going to be minus x to the minus 1.
Exactly.
Yeah. Plus.
It's going to be difficult, but I'm going to write it as minus 1 over x out of habit.
Yeah, that makes more sense.
It doesn't. I mean, minus x to the minus 1 is perfectly fine. It's purely a matter of taste and habit. Just habit.
Yeah.
Kicked in there. So, and here?
Minus 1 over x.
Good.
And 1 over x.
Yep. So, to make this equal sign okay again.
That is, that's going to give -1 over x squared. I think so. We need to plus 1 over x squared.
Absolutely. Which we've all already decided how to do.
Yeah, with -1 over x.
Yeah. So now the whole of the top row is going to be the integral of the whole of the bottom row, which is equal to what we were trying to integrate.
Yeah.
So we're done. Oh, not plus c, because it was a definite integral. So between those limits, 1 and e, we can factorize it. We could take minus, we'll have to take minus out, won't we? Well, we won't have to. And then inside?
It's -1 of it. Ln x -1.
Well,
ln x plus 1.
Yeah, good. Between 1 and d? And what do we get?
You get -1 over e times 2.
E times 2, yeah, good.
And then minus 1 times 2. No, -1 times 1. So just -1.
Yes, but we are subtracting, aren't we? Or is it? Pardon me, I might be wrong here.
Sorry,
log of 1 is 0 plus 1 times.
It's just going to, with 1, it's just going to disappear. It's going to equal 0, isn't it? I think -1 over 1 would give -1.
Yes, it would.
Times.
And then we're multiplying by a total of 1.
So it's going to be -1, which is going to be plus 1. Yeah.
Yeah.
So it is -2 over e plus 1.
Which is what they wanted here, isn't it?
Yes.
Shouldn't surprise us. Good.
Yeah.
Right.